I'm Nathan Harding. I'm Chief Executive Officer of Exobionics. If you've been on the high-tech company event tour lately, you'll know me as the guy who goes on after Rodney, which is good to see you again. I'll just say what we're going to do first is we're each going to take 2 minutes to go over a slide we have about our own companies and what we're doing, and that'll give you an idea of where we come from in our responses to questions. So at Exobionics, we see the world as a world that's facing a gigantic wave of human augmentation. And we think that that's so far been things like hearing aids, but it's about to get much more exciting because the IT revolution has really enabled a very rich interface between human and machine now that allows us to do amazing things. And you're going to see people running faster, jumping higher. I think for me, it's going to culminate when you see grandma at the mall showing off her new Exo pants that allow her to take a walk with her grandchildren that she was too tired to take a walk with before. And we work in the military market with Lockheed Martin, and we work in the health space. We have a product that's been out in the market about 20 months. We've got 47 units around the world right now. And they're sold in rehabilitation centers, and what they are is they're human exoskeletons, a wearable robot that you get into, and you can stand and walk. Like, for example, if you've recently had a stroke and you need to relearn how to walk.
Well, thanks for having me here. I'm impressed everyone powered through till the evening here. My name is Morgan Quigley. I'm with the Open Source Robotics Foundation. We're a small Bay Area nonprofit. And I'm particularly interested in how we can improve the collaborative authorship of robotics software. So these future applications of robotics that we're thinking about in the near term to near distance to maybe even distant term, things like being able to do home assistant robots where we have a picture there, the big picture of a robot over at UC Berkeley. So these tasks in general, we can look at them, we can call them loosely defined tasks, such as, here's a pile of laundry, please fold it for me. That's very different from these hard-coded tasks that Rod was talking about before of, here's a car part, please weld it in this exact same way that you did the last 10,000 parts. So these require enormously complex software, dynamic software systems, and quite frankly, in my opinion at least, they're too hard for any single lab or company to write all by themselves. And so we need to enable collaboration with peers and with even end users and customers perhaps even. So we've developed over the years this robot operating system, or ROS platform, to try to smooth this process of collaborative authorship of robotics software. So what we're trying to do is create both a flexible middleware as well as a suite of tools and capabilities that you can pull off the shelf to do common things that are needed in modern robotics. Lots of these problems, such as computer vision, for example, are open problems. If you go to the nearest computer vision conference and ask 10 people, how do you solve this problem, you'll get 10 answers about their method's the best, and they can't possibly imagine that there'd be another approach that was better. So we've tried to be agnostic to that and have this framework that you can plug in algorithms, try things out, plug in something else, try that out. And what we're trying to do is eventually build a community around these advanced robotics ideas of, now, can we hot swap these entire subsystems, bring things in and out and try them, and really enable rapid prototyping of these complex robot systems. So we have a few tens of thousands of users now. It's always hard to measure in open source. We're a BSD licensed product that's just kind of out there on the internet, but we ballpark it at a few tens of thousands of people around the world trying to build these collaborative systems.
Okay, I'm Ken Salisbury. I'm in the faculty at Stanford University, jointly in computer science and surgery. I think throughout my whole life I've been interested in hands. I found a finger in my mom's house that's made of plastic when I was 6. So I kind of want to give the context that maybe will help with my comments later on. And you can kind of see, 4, 5, 6 threads that go horizontally across. The left vertical column is older robots. Like there's a Unimate near the top with sparks coming out. That's welding. There's some teleoperators from the early nuclear days. I can't see everything on this thing, but just a moment. So going horizontally, we have robots, robot arms. You can see next to the Unimation welding robot, there's the Puma. Then there's a surgical robot that we started in my lab. Next to that is the WAM robot, which was able to catch that ball at 80%, that orange ball, 80% of the time for a while, which was, I think, a record. That arm turned into the WAM arm at the right, which is sold commercially. It was picked up by DARPA to be combined with a bomb-disposing hand, in fact, one of which Morgan had significant impact on. The intuitive surgical robot is interesting to me because it's a human extender. It's got some autonomous capabilities to not bump into certain things, to slow down in certain circumstances, but really it's capitalizing on the human skill and judgment. And I think this zone between pure autonomy and pure human controlled is the really interesting one for the next many years, where we add more and more local autonomies, like an autopilot. You can fly the autopilot instead of worrying about all the other parts of it. We also do surgical training. Simulated, we take scans of real people, we let the doctors rehearse on that scan, and we haven't done clinicals yet, but the notion is to let them get ready for the surgery the next day with patient-specific simulations.
So, I guess I'm kind of the outlier here. I'm really a neuroscientist, and I helped start this field called neural engineering, where we take engineering approaches and apply them to neuroscience. And one of the things that we've done to do that is to try to understand brain function. And what we found in the last 25 or 30 years is that it's a departure from the usual way of thinking about brain function. For many years, the brain's been modeled as a machine. And what we're really starting to understand is that, of course, the brain's not a machine. And what does that mean? What it really means is that instead of being modular, the brain is highly non-modular, so that many parts of the brain are doing very similar things at the same time that each neuron is doing many things. And so it's really very difficult to point to different parts of the brain and assign function. And what that means is that the causal trace becomes very difficult to identify. So what we're on the edge of now is sort of a revolution in neuroscience, where we're looking at the brain as a highly complex system and trying to apply tools to understand how it works. And we've made some progress in that, and the progress that in this idea of neuroprosthetics, where we extract meaning and intention from brain signals and use that to control robotic devices like prosthetic arms. And the success that we've had in that is directly attributable to our new understanding of brain function.
I just want to say one thing. I meant to shout out to Morgan that the Baxter system is based on ROS, his robot operating system from OSRF.
As we get into questions, I want to mention one question first and then come back to it after you guys have had time to think about it, because I thought it was the best question that got submitted, and it's really interesting, which is, for what accomplishment will the first Nobel Prize in robotics be given? So I'll let that go in your brain while we're talking, and then we'll get back to that later. I thought that was an interesting idea. I have a question that I'm really interested in, and especially I think it's appropriate after the Baxter presentation, and that's that right now we're kind of seeing this barrier go down between the robot and the people. And the question is, how do you characterize a machine as safe for that to happen? And we've always kind of wrestled with that fact, of course, in what we're doing, because you actually wear the robot, you get in it. And I'm wondering if you guys think as an industry that we need to come up with the standard first before potentially someone gets really hurt, and then people start pushing a standard on us that might be overly restricted. Rodney, maybe you can speak to that.
Well, there's a bunch of standards for industrial equipment, in the industrial space. We're having to figure out how to extend them to cooperative robots, collaborative robots. And there's some tricky parts with that. One is to make the arms not be able to even potentially move with more than a particular force or acceleration, but then you get to the problem, people say, what if the robot has got a knife? Then, if it can put the knife, in someone's eyes, it's got to be a really low force. And I say, don't give the robot a knife, but Cornell University, Cornell, who has one of the Baxters, has been giving Baxter a knife and trying to train it not to stab people. So there is always a problem, and it comes down, I think, ultimately there has to be some judgment, because you can't guarantee any particular machine will not cause injury in some way. A car will cause injury if it's used wrongly.